Yeah. So we can start now. So the next speaker is Rafael Gonzalez. He is the one that is guilty of making me interested in any of this. Otherwise, I wouldn't be here. So it was Rafael who some years ago asked me about topology in physics, which I didn't have a clue. I didn't understand anything. So because of him, here. So Rafael was physics student in la Universidad Pedagógica y Tecnológica de Colombia in Tunja, in the north of Bogota. Then he did his PhD in the National University in Bogota. And then he was hired in Universidad del Norte, but he's been in the group of Hydrosinova in Mainz and works very closely with Libor Smekal, who is in Dresden now. So he will tell us about topological basis in altermagnets. Rafael.
Thank you, Bernardo. And thank you for all the work that you did in this organization. And yes, I'm going to talk today about this altermagnets with a new topological. We found some, this is a work with Bernardo, actually, this connection between topology, Bernardo's expert, and altermagnet. That was a new phase that we discovered in Mainz 4 years ago. And let's start with what is the altermagnets? What means this new magnetic phase? Okay, we know the ferromagnets. We have these magnets in our devices, our drive, and iPhones, and we know that these magnets have these blue points represent the magnetization, the local magnetization. We have a net magnetization by unit set, this like 12 unit set, for example, in 2D. And this interaction with these atoms produce a symmetry break in the type-universal symmetry, and we plot the energy bands for any magnet. The total magnetization generates this similar splitting, a similar field in the band structure, and so this splitting the. In altermagnets, it was discovered, I don't know, in the 60s, actually in the 30s, but was people believing in the existence around the 60s with the neutral diffraction technique was discovered. And we have this, for example, this unit cell that have blue and red points means up and down or plus and minus magnetic local magnetic moments. And in these cases, usually the connection with this local magnetization is due to time reversal combined with inversion or combined with foundation. And we don't have a net magnetization, and if we plot the energy bands from BFP or any type of model, we notice that the energy bands are degenerated the full Brillouin. 4 years ago, we found this was discovered in new phases that is similar to the antiferromagnets, but now if we saw the non-magnetic atoms in the unit set, for example, these black points represent oxygen atoms, for example, another non-magnetic atom. We notice that we break this time reversal combined with inversion symmetry. And we have now a new symmetry to connect these two opposite magnetic atoms. That is the rotation combined with time reversal. In this case, for example, you rotate 90 degrees and apply time reversal symmetry that change the blue with red. And in these cases, you have now plot the band structure. You notice that you have some splitting in some particular direction. For example, if you have 90 degree rotation, you have, if you move in the x direction, you have the red points in one direction, and the connection with time reversal by 90 degree rotation, you have the blue, the down channel in the opposite. You break time reversal symmetry effectively in the band structure. You have something that is similar to the ferromagnet, but the total magnetization is equal to 0. We saw that we have some anisotropic symmetry in this kind of altermagnet. And this was like a hidden phase for around 90 years that usually in DFT we saw some publication around this spin splitting, and nobody take care about the symmetries and the origin of this spin splitting in this kind of manner.
This is a three-dimensional
Three-dimensional.
crystal, and the spins, which direction they go?
With this one particular case, this without the spin of the coupling. This is something that is origin without the spin of the coupling, which means that it's independent of the direction of the spin.
So the lattice they can point anywhere.
Anywhere.
So you just fix them, the tiny magnetic field.
Yes, definitely. You have the only condition that you have opposite local magnetic moments, and the direction is not important here because there is no connection with the lattice. But you have extra atoms in the unit cell to break this TP symmetry, and the connection is C4T symmetry in this case. And if you this is very important. It's no the splitting that is not what do it to spin of the coupling. Splitting by the exchange direction. That is really interesting. That is the most important thing.
But afterwards, it's stable under small adding of the spin moment.
Yes. We're going to see that this is stable. If you, for example, apply spin of the coupling, you see some, for example, these beginning points actually still slightly. But you notice that the origin of this splitting is not spin of the coupling, and it's this C4T symmetry of this splitting. We saw, for example, a spin Fermi surface. We can separate it like something like we physics connect with the shape of the orbital, the S wave magnetism, for example. We have legendary here, and we call, for example, for this case, we have this D wave altermagnet, because the way that the splitting is in this 90-degree rotation. Yes, this is quite famous. This now in the literature, this kind of splitting, the paper of Libor in 2022, that created new name for these new phases. But I'm going to talk about the story about this demagnetic phase. And new phase, I worked with Libor and Iron Thomas 6 years ago, actually, these topics. But this new field in magnetism opened a new door to explore, for example, topology, magnonics, spintronics, ultra-fast optics, because this kind of magnetism is 1,000 faster than the normal ferromagnet, for example. Thermoelectronics and different fields now in the matter is focus in this new field. In particular, for example, the connection with superconductivity is now that a really hot topic in the conversation field. But now we are going to talk the connection between altermagnetism and topological. This was an explosion about this field in 2024, for example, in 2024. The Science magazine showed the list of the 10 breakthrough of the year, and the only the physics was this new magnetic phases. Also in the economy in 2024 and in different medias was announced this new magnetic phase. This altermagnetism, like a new type of magnetism. Actually, in one of the Saturday night shows in US was shown this the altermagnetic phase. I'm going to put here because it's we don't have time for it. Okay, let's talk about the story of the altermagnetism and some connection now with topological materials and some DFT calculation to do this in real materials. Okay, I'm going to talk about the story of the altermagnetism is really highly connected with the story of the Hall effect. We know that the Hall effect is we have, for example, the anomalous Hall effect. We have for iron, for example, if you apply an electric field in this direction, and we have electron move in this direction, they deflect either to the external magnetic field or the local magnetic moment of the iron atoms, for example. We have also, we talked today about the spin Hall effect. If you apply a correct charge current, you could see as in some cases you can see some spin current. Usually this spin current is connected with this deflection of the electrons, speed of the electrons with the still recoupling phenomena, for example, in platinum, that is really the topic of this the example for this spin Hall effect. And we also hear today about the quantum anomalous Hall effect, the quantum Hall effect, sorry. That is really nice works about this topic in the 80s. And we know that the connection between the transversal conductivity with this amazing work with Toll's others that this is related. I call this efficient number that is related to integral of the variable in the case space. And this also actually was a topic of the Nobel Prize in 2016. Okay, in the beginning of 2006 and 2030, we have this quantum anomalous Hall effect in real materials. In this case, in thin fields of chromium, doped, bismuth, selenium, and antimony materials. That is the quantization of the conductivity as a function of the chemical potential for this kind of systems. And also, the experimental was noticed also the quantum spin Hall effect in Calvin telluride quantum bands. Here, for example, if we have some particular thickness of the mercury telluride, we have the measure of the quantum spin Hall effect was given in 2006. In this paper, they have a really nice model, type 1 model, to explain this quantization, and we are going to use this like a basis of the connection between quantum spin Hall effect and altermagnets. Okay, finally, in the 10 years ago, we discovered also the anomalous Hall effect for no collinear antiferromagnet. For example, we have this magnetic cycling that is from no collinear antiferromagnet, like a kind of carbon-lattice that will be curious to tomorrow about this kind of lattices. And in this case, we have also the anomalous Hall effect, and we need an extra term in the transversal resistivity of the formula because it's not dependent on the external magnetic field, it's not dependent on the total magnetization, as extra term in the conductivity. Yeah. This was measured for the material 10 years ago. And finally, the question we delivered some years ago, 2008, 6 years ago, was it was possible to have an anomalous Hall effect in collinear antiferromagnets. And this was an idea of Leo that was in this time, he was studying the symmetries and say, okay, maybe it's possible, maybe it's not. And I did the calculation for ruthenium dioxide. That is the diagonal unit set that we have 2 atoms, 2 magnetic atoms of ruthenium, and 6 atoms of oxygen. And if we calculate the anomalous Hall conductivity, we notice that in the Fermi level we have values around the 30s, 40s cm by centimeters. That is similar to the ferromagnets. At the beginning, we don't believe about that, but we will study the symmetries, and also we propose a type 1 model. And definitely, this is a new. This was a real quantum anomalous Hall effect for collinear ferromagnets. Unfortunately, this was not the best examples. Now, it was the first example for altermagnet, but now the community noticed that this is not real. They don't have local magnetic moment in these crystals. But was the first example for altermagnet. If we have an anomalous Hall effect, means that we break the time reversal symmetry in the Brillouin zone, in the reciprocal space, and we notice, for example, during the spin projected Fermi surface from DFT for this this is one structure. For example, we move gamma S, we have the splitting, we call flow gamma minus X, we have the opposite splitting. This is the valence structure without spin-off coupling. If we add spin-off coupling, we saw some small splitting, but the splitting is really huge. It's almost 1 electron volt, and the spin-off coupling for generate splitting less than 100 milli electron volts. And this 10 times, 2,000, 10 times or more than the usual spin-off coupling. And this emitter breaking started, in particular, this calculation from DFT of the in infrared surface start to generate this new non-relativistic physics in the spin splitting system. We call it altermagnetic. Remember, we don't have net magnetization, but we have a spin split in the region zone. And this was the birth of the altermagnetism, because with that we start to study, for example, if we apply electric current in the diagonal of this fine surface, we can generate spin currents. If you generate spin currents without net magnetization, something that's really interesting for the industry right now. And also we noted that we can generate transversal spin current, because if you apply, for example, the electric field in this direction, you have extra red to the right and extra blue to the left, and we have a transversal spin current that is not dependent on spin of coupling, that is something that is spin current, not relativistic spin current. We call this the spin splitter effect. Okay, and it's possible, for example, generate Jagged magnetoresistance and other effects that now are really a hot topic in condensed biophysics. Okay, let's move now to the connection with topology. Okay, this started in 2022. In 2023, we start a lot of work with connection with topology. This is a few lists. I don't know, right now it's around 100 words with around the 100 word topology response. In one of them, we were with information here in the US that the way to obtain materials with altermagnetic and topological response. But today we have also, for example, connection with the Majorana, for example, in 2024. We find with Bernardo for the general bilateral lines of materials. But today I'm going to talk with these two words that we listen to with Bernardo, that is the spin numbers in altermagnets and the model Hamiltonian in altermagnetic momentum. This is focus my talk in these two words. Okay, let's start with the BHC model. This is the model of the quantum and also quantum sprinkle effect. We have, for example, this is the top view of the titanium dioxide. We build the type bonding model in X, for example. We have these oxygen atoms that generate the asymmetry between the interaction in X and Y. We have two orbital by side with X state and P state in each point. This is the on-side energy. This is the interaction in X, interaction in Y, and this is also this is intra-orbital hopping, and we have also the interorbital hopping like G1 in X and G2 in Y. We're going to generate altermagnetism to put the anisotropic interaction in the hopping parameters K1 and K2 mainly, and now if we rotate the unit cell, now this is for the up channel, and for the down channel we have the same. Now we have the interaction, for example, K2 is in X and K1 is in Y. It's exactly the same Hamiltonian, just that we rotate the C4, we apply the C40 rotation and time reversal for this part of the Hamiltonian. This means that we have now 4 orbitals, 2 for up, 2 for down, two sides by orbital, orbital by side, sorry, and this will be our system. Now we control the altermagnetism for this K2 and K2, K1 and K2 parameters. That is measures the
what's the difference with respect to the P plus IP superconducting model? Same.
Oh,
I mean, the off diagonals we have Px and plus I Py, if I understand right, and on diagonal it's just Laplacian and the mass of the particles and antiparticles.
yes, this is just the combination Px and Py orbital. It takes it on this magnetic push sign Hamiltonian. This is exactly the same. I think so that I really don't know the connection between that and the superconductivity.
So I think you just superconduct in case you're talking about the theoretical comparison, right? Whereas here it's in the Hawking. No? The Hamiltonian was the same. I mean, for me. Anyway.
Okay, I need to check. Okay. No, it's exactly the same that I need to check it actually. It's exactly the same of the quantum statistical effect, just that we apply this extra symmetry. And the final, we have two block Hamiltonian with up and down channels that is connected by the 3/4 symmetry. And this a couple channels, the constant channel, and we have this is the spin. Actually, the Hamiltonian commute with the spin operator that our spin operator. Okay, first we reproduce the same result of the manganese and cadmium telluride, mercury telluride. We could, for example, K1 and K3Y1. We don't have anisotropy interaction in X and Y. And we notice, for example, the quantum anomalous effect, that is the quantum anomalous effect, spin effect conductivity as a function of energy. We notice the energy topological band gap is due to this signal. Also, we plot the surface state and also calculate the zeta 2 index with the eigenvalues of the inversion symmetry operator. We notice also the Kramer delivery.
We're going to put M0. M0 must be 1.
As we know, so okay, I forget here the value of the this M0 is very important to know the differentiate. Now, for example, we use different K1, for example, 1.05. We have this splitting. We have the topological, but they have survived for this altermagnetic splitting. And now we have, for example, the middle splitting also from the surface state. And this is a picture of the spin texture that we have also this C4P symmetry of this system. But now we have the combination. We have this topological gap and the altermagnetic splitting just with this anisotropic interaction. The idea is to study how calculate, for example, the zeta 2 index in this. In this case, we have inversion symmetry. We can use the inversion symmetry operator to calculate the eigenvalues. But in other cases, it is possible to characterize this topological phase with another invariant, for example. And the answer for that was the work of speech and numbers. And here,
You have the answer in the past.
just in the past. We can calculate, for example, the spin spectrum for, I don't show here, but we can, it's a representation. We can calculate the spin spectrum, the Hamiltonian commute with the spin operator. We can project for the occupied band the spin operator and calculate the Chern number for up and for down when it was separate calculation. And calculate the spin Chern number and the Chern number for up and for down channels allows to calculate the spin Chern number. That is a signal to the zeta 2 index and also for the spin component. And now, I don't show here, but Bernardo demonstrated that this is a strong topological invariant for C4T symmetry using K theory. I don't show here because it's John Bernardo. More than for the DFT community and 500 models. Okay, this is the topological phases. Now we can change. You use, for example, a small K1, and we can change the mass term, for example, and calculate the bands. We can see this is the spin projection of the highly occupied bands, and we notice, for example, nodal lines in this protected nodal line for C4 symmetry in this direction. because we need to rotate 90 degrees and change the color, change the skin, which means that each 90 degree we have annual light protection by symmetry. For some small values of m, for example, we notice that we have extra null line around the gamma point that is due to the it is determined by the G, the relation between G and K1 factor. We have extra null line the result, but we maintain our C40 symmetry. Okay, if we want to calculate, for example, the Chern number, we could plot the very curvature. In this case, we plot the very curvature, and we notice that the integral of the very curvature is zero. We have two regions, one plus and one minus region. But if we integrate just in part of the region, we have half of the region, so generate half of the Chern number. That is meaning that the extinction number is actually a really good quantum number to describe this kind of systems. If we plot also the projection of biorbital, we notice one of the signals of the topological material that they have this band inversion. For example, for n equal to 1.7 is close to gamma, but for 3.4 it's close to x and y points. This means the band inversion is changed in the region zone around you when you move for different M0 in this case. Let's see, we are talking about H correspondence, boundary correspondence here. And in this case, for example, we plot here we have the trivial case. Actually, this is not the state in the band gap because we have a trivial band gap, so insulator in these cases. For different values of n, we have different shape of the H in the H that represent the state in the band gap of this kind of altermagnetic system. This is the case that we have small anisotropic, but in the interesting case appear when we have, for example, K1 1.3, that we have stronger anisotropy or altermagnetic anisotropic current. In this case, okay, we have also our spin texture, so we have also our trivial cases. But we have to start to notice that the H start to be spin polarized. And in this region, for example, we have some particular H state that is spin polarized for one channel in opposite phases, and 80 degree rotation have different spin polarization. That means that we have here, we have in this case a relatively strong anisotropy, altermagnetic anisotropic term. And here we have some part that the spin Chern number is not this kind of phases is we are trying to now to study the Serrano because it's interesting from the point of view of physics because we can apply electric field and use these states to transfer to things. Some people say that we can use this to H-turn, use the H2 transport spin and just one kind of spin polarization. The question here is we don't have a spin Chern number, but we have the H state surviving in this case. We study now this.
Sorry, what is the symmetry there? Because you have this space in the both places there is some symmetry.
C40.
C40.
Okay.
C40 symmetry.
But if you put one more layer, which from the blue and the red, if you put one more layer on top,
if we know a square, for example.
if you
Just
add one more layer, is stable or you can fluctuate where the red is and where the blue is?
Yeah, this is the two cases. Depending if the next layer is coupling permanagnetic or anti-permanagnetic with the two layers. This depends because you can start to this is two resistance that you can start to layer by layer. If you have the same direction, maybe you can have walls.
But how about doing this and this? Is it stable? Bigger? Yeah, bigger.
Stable. Stable. This is stable. There is something. This is something that is very stable. Now we can move to the DFT calculation. How to use this to build a real material. Actually, I work more with DFT. I like to show this picture about Professor Walter Kahn, developed the basic equational theory. And okay. If we have, okay, we are talking about 2D systems. We think about 2D system. If we have one 2D system, for example, one bilayer or monolayer, usually this kind of system have PT symmetry, which means that we don't have the altermagnetic splitting. In this work, we propose different paths to generate the altermagnetism into the system. One case should be, for example, if we apply electric field, we break this PT symmetry, and we can generate the altermagnetism in this kind of system. We can also grow the material on the one substrate, and you can also break the PT symmetry. And the option that we study here is we call the Janus. So people know that the Janus material that is change one layer of the 2D system by another kind of atom and break the PT symmetry and induce the altermagnetism. And this was the case for manganese phosphorus selenium 3. Substitute one selenium layer by sulfur or tellurium and study the altermagnets. Let's study this case. This is the monolayer of selenium ion. This is the band structure. The system has PT symmetry. This is square lattice with up and down channels. The green ones are the selenium. This is in one layer of the layer that we have here. We don't have any splitting, but when we introduce the tellurium atom in the bottom of the monomer layer, we have used some chemical asymmetry of the system, and we notice now the skin splitting is not in the super. This is the calculation without splitting. And the splitting starts to change with the strain. For example, this is Janus because of the two phases. This is that equal food for this kind of materials. And this is stable also. It's on the activity and thermal stability was calculated also. And in this case, for example, the quantum anomalous Hall effect is noticed in the band gap. For example, band gap is induced by spinor decoupling. It's small band gap. But we notice, for example, this also band inversion. And in this band inversion, we notice, for example, that the Mx is due to the dxt orbitals and My in this part is due to the dyc orbitals. This is a similar shape of the spin splitting, the spin projection for the valence band, the valence band. And now we have this proposal for iron selenium tellurium monolayer that have altermagnetic splitting. This altermagnetic splitting that we show here, and also quantum anomalous. If we calculate the H state for the real material, we notice, for example, that they have similar, like strong anisotropic term in this real material that we have changed C40 symmetry for the H state and changed by C40, and it is the state that generates this quantum anomalous. Quantum spin effect. And it's not perfect. We have some, for example, here some orbital, but it's the real material of the calculation. We have some more like 30,000 wave functions in this case.
Can these materials be produced in lab or not?
This was produced in the lab. The iron selenide was produced some years ago on top of another material, but the homework for the experimental team is try to do this kind. I know that some experimental teams do these young materials, but not with iron selenide. I know that this is stable. The pure material is stable, but now this is some proposal to experimental to do this gel. Yeah, it was PhD in this work. Now we can move to the 3D systems. And in 3D system, we start to put the interaction in this with different layers and put the interaction in the Z-axis. And the simple case was a simple hopping in the Z-axis. In this case, like that. But we have this kind of interaction. We noticed that the material start to, for example, for n equal small n's, the material has like 5 centimeters in the gamma. Yes, this ys in C parts. We have n large value. We have a direct centimeter. We have also we notice also that altermagnetic split in some regions that we can solve. We have also we have protected data points or value points for this kind of system. And we increase m. We have a really strong on-site interaction. We have a trivial material. We don't have a topological insulator in these cases, but we have direct centimeters and centimeters. And how characterize these systems in 3D? You use again the extinction number. Now we calculate the extinction number for Kc equal 0 and Kc equal R. In Kc equal 0, we have this purple line. That is 1 in this region for m. Start to change to -1 in this region for m. And for Kc equal 5, we have this green line. And we notice, for example, here that the topological response is characterized by the extinction number in the Kc and K0 planes, because we calculate by plane the extinction number. However, if we include, for example, now one mixing between layers, for example, this term to perceive also C40 symmetry. We have an extra term by mixing the spins. We have now the one topological part, the fine structure. Even with the E small, now we don't have this commutation, but we can also use the extinction number to characterize this phase. And the phase diagram looks quite similar. Okay, the phase diagram. The phase diagram is exactly the same, but now we have a topological graph. And the material is a topological insulator, but something curious starts to appear in the spin spectrum, for example. This is the picture of the spin spectrum, and for small values of n, we notice that we have 4 spin by points in the Brillouin zone, and for m equal 2.1 or from 1 to 3, we have 2 spin by points in the Brillouin zone. These by points in the spin spectrum.
Yeah, what do you mean by spin spectrum?
The spin spectrum is the plot. Maybe I have here. Here we have the projector of the occupied band. We calculate the spin operator for these occupied bands and we solve the eigenvalues for this.
So the difference is
and you obtain, for example, usually you have this, you plot the spin operator in the balance band, the Brillouin zone, in the part of the Brillouin zone, like the bands, but now you plot your spin eigenvalue, and usually you should have ±1. If you have electrons ±1, but when you have a spin decoupling, this spin start to mixing. And in topological cases, you can have this the mixing could be something like spin by points. That how we know that we have this spin by points? How? Because we notice that the extinction numbers start to change when you calculate for different KC. For example, here for different KC, we notice that the extinction number changes twice. And in this case, the unit of the extinction number changes minus 0 to 1 in one, sorry. This means that this extra charge appear for extinction number.
So it appears exactly at the two transition points of this 5 point.
Yes, you also see the two transition points. Yes. In the spin spectrum, you notice in this particular KC points. And this means that actually this is one way to characterize strong topological insulator because it's one here and 0 here, the extinction number change in one, it means that's strong topological insulator. And here the extinction number change twice, then we call this the weak topological insulator because we will not change twice. Actually, for example, the theta twin is for this case, it should be 0. The extinction number is the extinction number change points. And we plot the surface state. Sorry, we know that the surface state, in this case, are corner states in this part of the region. In the topological insulator, we have surface state in this case. And this again is characterized by the change of distinction number for different cases. If we plot also the spin projection for 3D for different cases, we notice here the robust shape of the spin splitting in different layers of the KC index. And here we notice, for example, the change the color of the spin for different planes. This change of color is connected also with the change of the spin. Let me check. This means that we can, using this construction, we can have also 3D topological altermagnetic topological insulators, even if we don't have this preserver Hamiltonian, not preserve the commute with the spin, and we have this C partition.
What was the N0 again? Which parameter is that?
N0 is the on-site term. Is the on-site term. This is the
I understand. Yeah, of course.
This is the master.
Yeah, sure.
This is the master. Yeah, we can control each phase with just this parameter actually. And but now in this our Hamiltonian we have extra parameter that is the altermagnetic. Chern. Okay, that is with that. Maybe characterized we have this for this protected symmetry, this for this indices, this 3D topological insulator material. We have different, we can also have blue, red, maybe depending on the end. And maybe it's quite really important for spectronic topology or spectronic community. Okay, with that, we have short summary review will take more time. The extinction is a quite robust topological invariant to using altermagnetic system, for example. This is one conclusion. We can have this 2D or 3D C4T symmetry that display quantum simple effect, also characterized by extinction number. And these two materials could be used for extinction number, not real extinction number, not quantum simple effect in real materials. We are now looking for another candidates, maybe easier to build. Here in this gel material, I got thanks to Leonardo and my colleagues in mines.